Good afternoon. The delight to come to be the speaker of the Xiaodong
This is really thanks.
Okay. From University of Washington. He did his PhD in topics at University of Massachusetts. Then he switched to condensed matter after postdoc at Cornell and Boston. One of the things characterized his career is that he always opened up new chapters in new field. And for example, in the two-dimensional materials in the period of 2012, 2013, he really pioneered the 2D electronics and semiconductor structural topics that in the field of optical. Together with his colleagues, he has formulated unique Valley contrasting physics, monolithic transition matter dipole organized. This work laid the foundation of 1 decade of very, very active research for the matter. The second, then he moved on. The second field was really exciting. He had started his discovery of 2D. He became sometime around 2017 and 2021. He really demonstrated quantum triadi is the 2D magnetic integrator, the unique layer dependent magnetic state. This work initiated the field of 2D magnetism. Then last 1 to 2 years, we pioneered another really exciting direction. Quoted from prominent colleagues who said, "But didn't think we can be able to see that," and he thought he made that happen, that the realization of fractional quantum anomalous for that. He discovered spontaneous magnetism, quantum anomalous fault, and fractional quantum anomalous fault. He fixed it by the Monica Carroll. And today you can see from his titles, he made another really revolutionary discoveries using optical method to study the fraction itself. So this is a person who always opened up new chapters for many forms. So his accomplishment widely recognized is one of the most respected physicists in this field, and of course he was very young, is already getting enormous amount of and awards. Among them is the Vernier Bush Family Fellowship and also National Academy Scientific Award for Science Award for the Scientific Discovery in 2025. So,
well, I thank Jain for the wonderful emergence. Today I'm going to tell you something we're going to tell you about. You probably noticed, right? Actually, I also just noticed I put these October 18th, but from the inside. The reason is that I was here last year, this time give a 7. And I want to remind you that there's only 1 year past, means it's difficult to achieve a breakthrough with you. So you might hear something which I talked about last year, that will be upset. So that will hopefully come from the beginning. So today I'm going to tell you how we can use legs to measure the current charge. So the topic itself is down to the broad field of condensed physics. I think one feature of this condensed physics is that the field itself actually really coupled to the development of technologies. So a great example right, is discovery of the transistor. We spring back to the 1940s and these 3 gentlemen developed, where they studied such a quantum context in semiconductors and found the concept of these transistor effects. So this the example that together we started developing the field, really revolutionized these microelectronics, where from vacuum tubes to tabletop and these computers, laptops, phones, etc. So here I highlight these the roadmap of the transistors from TSMC. right? Last decade, you can see that the size of transistor already improved, right? From this 28 nanometer, and now we have about 3 nanometer to 2 nanometer sizes. So during these still of the transistor technologies, actually, they are also associated with the discovery of mathematical physics. One of the great example is the discovery of this integer quantum effect. Let me see if we can. See. So it's still go. Let me try one more time. Okay. Great.
Oh, speak and do it.
So this that we discovered using this silicon MOSFET in the beginning of the 1980s, right? We know that the silicon MOSFET because these anomality to the electron gas. When we apply a large magnetic field and equal to these two systems and measure the optimal activities, you will find out that the optimal activity actually is complex in these number of these units of E square H. And then here in the front we have C is an integer. So that's the integer quantum. A couple of years later, the material system actually improved. Now it's in the gallium arsenide systems. And the electron quality actually improved quite a bit. Then what it means is that the electron-electron interaction now becomes important. And when you measure this quantum again, you'll see that it's not only quantized in the unit value, it's also been quantized in the fraction values. Okay, so now we have this fraction quantum effect. The discovery made actually by Bob Bradley to understand what is the wave function of this fraction quantum effect, what you feel that it's amazing wave functions, and also that what's important for these fraction quantum is associated with these fractionally charged excitations. Right, we usually see these kind of cartoons where you have one electron split in three. But what it really means is it's a function, it's a property coming from these electrons. So, in addition to this fractional charge excitation, what's interesting about this fractional quantum state is that there is also a manifestation of another exotic particles called anyons. So, in a two-dimensional limit, we can sort of understand the anyon using these distinguished particles that these two positions R1 and R2. They can represent the wave function as psi and R1 Now, we swap the position particles R1 to R2. Then these two wave functions now become psi R2 and R1 connected to the original one with this phase e to the I theta. So from quantum mechanics, we know when the theta equals 0, then these two wave functions same. So this is the boson, right? And when theta equals to pi, then this is a fermion. But in a two-dimensional, theta actually can be a rational fraction of pi. Now, the particle itself has this fractional series, okay, with this phase. And now this particle is known as a anyon. So originally, anyon was just a very abstract mathematical concept, but the discovery of these fraction quantum states leads to the community to realize actually the fraction quantum excitation itself is anyons, right? That's the pioneer works from Bert and from Belichick and so then the sample mobility keep improving, and then more states has been discovered in the fraction quantum systems. Then the community realized that in addition to these original anyons, there also can be non-abelian communities. So what's thinking about them, right? Not only they're fundamentally but the anyon can be used for these fault current computations, found out by. Yeah, we know that there's a lot of activity going on in Stanford for doing the quantum computers, using quantum computers, using superman computers, etc. But there are always an issue, right? Because the challenge in the field is about the error practice. So the campaign found out is that for anyons, actually they're immune to these quantum errors. The reason is coming from the wave functions of the anyons actually the wave functions depend on its position in experience. Therefore, they are immune to this local operation. If you really want to change the functions, you have to do this grading operation to scrap the position of these particles. So that's why the system itself is immune to this local variation, which may source the quantum difference. So now you see that we have anything else. We have a theory. So why is alien quantum theory has not happened? Well, because not every alien can use to use quantum theory. One use called parafermions. So theoretically, we can create this parafermion by interfacing a superconductor from reflection on how it states. So this is one of the proposals. There are a lot of efforts ongoing in the community. Here I have a paper from Philippines group in Harvard, where they have this anomalous graphene and the interface with these superconductor with neodymium electron. They're trying to introduce these they observe some interesting phenomena, such as cross reflections, excitations, but it's difficult to observe these power limits. So there's some kind of reason associated with this thing. The first is the fraction compound effect. It's a very good effect. You need a little energy to realize this effect. What it means is there's a little room to form an equation in country. The second is that when we try to assume that you is a success. We know superconductor actually doesn't like magnetic field, right? When you have a magnetic field, you can introduce the vortex in the system, will kill these power element states. Okay, so there's some fundamental limitation in all these schemes. So what we can do then, solve these challenge. Well, the solution is to remove this kind of idea, and hopefully can increase the gap of states. So we can realize these fraction compound states, but do not field not that much. So this is a fraction compound anomalous effect. Of course, I'm not the first one I'm thinking about this. There's a long history actually in the community to think about how to realize these fraction compound. In fact, we got a lot of analysis. So the first book actually still coming from Bob. He started formulating these ideas in the spin lattice, and there's a lot of work in the community after that to think about how to. But for all these proposals, you still need to ignite field to disperse the way to break the time reversal symmetry. So the concept of this zero magnetic field fraction compound effect was firmly established in the 2000 values. There are a number of theory work, as I showed you. So either you do modeling or you do numerical calculation to obtain these channels. The key concept to realize these effective the three waves. The first one is the band need to be topological. The second is we need a strong electron-electron interaction. And last one is also crucial, which is spontaneous tangle resistance breakage. Okay, so we need a solid magnetism instead, right? Because we don't find material anymore. We need something to break the tangle symmetry. In this case, it's need a magnetism. So in order to realize this. And the key is we need to find a system that can host these flat chain. Okay, band flat and solid. A lot of proposal has been formulated to realize these chains. And the system actually really working is on Morley supplies for people working in the field. Maybe you know that when you stack. Now, there is no twist of these lattice mismatch. We can have these Morley supplies. So the concept has been there for over a decade, but the field is really took off because of the discovery of these unconventional system activities by Pablo's group at MIT. So Pablo's group, by these results, they will show you that you can keep using these Morley and anyonics to found formation effect. But a sharp formation is not enough, as I mentioned, we also need a great kind of symmetries. So the breakthrough is coming from Davis group at Stanford. The 2019, they actually show that in imaginary holography, you can engineer these all lattice and into these contests and all of that. I still remember in there we actually presented these results at KIT. as well, into the mean, and we're going to display. And now we have three effects. You can use operation values to engineer correlations. You also can use engineer holds. Okay. Now we have the grades. So now we motivated by all these results. My group is starting to see where these directions start using slightly different system. And we'll be working on these and transition hypothesis so on. And that's a couple of theory we want to motivate our approach. The first one is from Alan McDonald's velocity. So when these paper shows that we have treated MOT2 bilayer, the top of the lancet actually is changing. So when you think about when we see lattice, right, and there's a lattice distribution, these lattice stacking, the distribution actually is has a spatial dependence. So we have formed these kind of pseudo. That's exactly what the Alan's paper pointed out. Okay, these layers so to speak is the origin of the biologies. And my collaborator among Yang, in Hong Kong actually, he also figured out when you have these layers so to speak skirmings, that correspond to spatial independent variations that leads to these pseudo field which has spatial independence, and they give us these real big topologies. So motivated by both, most works actually what they do is it's a single target picture calculations. So what it means is the system actually modeled by the honesty of the big models. It doesn't really come with those measures. The values, right? What it really does is not use these strong interactions in these just two values. And what they found out is that the system actually can be fractional change clear once you improve these strong interactions. And in parallel, right, we have a work experiment on Trinidad and with Leon Fu and MIT. They also point out the unisality settings, whereas these fractional change clear. So motivated by all this work, we realized, right, it's just that multi-field bilayer teams can post these fractional informing anomalous artifacts. And initially, our measurement shows there's two fractional states during minus 2/3. And in the last couple of years, by group and also collaborators, the S2 example shows the additional states in the system. Okay. And the effect itself actually kind of robust. As many groups around the world already see such an effect, and with many new effects has been discovered. What's exciting is that in addition to these strict MOT2, right, there's also another system emerged, which is a fraction, which is a pentagonal graphene and on FQAH and also bias. So this is broke down by Jain and MIT. What's exciting about these graphenes, in addition to these fractional physics, when you just change the device slightly, you can also observe the similarities, which is actually chemistry matters. So I think it's a quite exciting systems. So now we have two systems that the study is fractional physics. One is just MOT by it's the same. The other is individual by P, which is anomalous. And for the rest of my talk, I'm going to focus on these electricity MOT by. So let me just give you a little basics about these materials in case you never heard this before. Right? We're working with these transition metal diagonals. And the field is really discovered by Tony Hens in 2010. They show that the model MS2 is being derived by semiconductors. So actually, it's a time when I just started my own lab at the University of Washington. And my background was knowledge. So when I see Tony has this paper, I got excited because I know how to work with semiconductors. So we started my lab actually with just whole lab started working with MS2, and also very soon we found out that there's two additional similar kind of materials, which is MSC2 and WSC2. We also became really nice small semiconductors. So when I talked to my friends, like Wang Yao and Xiao, the March meeting, I said, we have these materials like MS2. What can we do with it? These guys are brilliant. Nearly best. Well, there's a look at these crystal structure of these small AMDs, right? And these two components of these hazards, right? One is copper, one is metal, then inversion symmetry breaks. Once you have great inversion symmetries, you should have these very dependent curvatures and also outward moment, and give you like these kind of very dependent outward slash inward excitations. And I think independently, right, there's a kind of theory experiments actually demonstrates physics. Okay, along with of course, Tony's group. So now let's go beyond just modeling. Let's say you have modeling and cut into a path, right, having two pieces and stack them on top of each other, and with one twist, we found these models. And in this molecular lattice, right, as here, we see in 1 million cells, we have two energy injection points. One when we call B, which is with metal on top of function. So in this case, we can think of it as a pseudo spin pointing up. And another is a C, which is the function on top of metals. And now we can think of pseudo spin pointing down. So these two pseudo spin energy injection, and they found these Hamiltonians. My colleague, my young person, he actually to use STM to map out these, pseudo spins. So the work in this particular data I showed is found is 2.7 degrees twist and multi-two barriers. The panel here shows the topographic image, and you can see these within more cells. You have these asymmetry MS point axial. And this metal with the high energy point. Then we can also measure these density states in systems. As I highlighted here, right? The density states is very low place at these MS and also XL. So this basically shows that the picture that is taught to you actually interact with right. Now with this understanding, what we first done is trying to show, trying to find out where the system can approach these So here's the diagram of the device. We have a twisted barriers, and during this dual gauge structure, so on top and bottom gauge goes on the plate. Then define this filling number in mu. The filling number is the number of carriers from within cells. Basically, I can use the two gates, right, to develop the systems. To probe the magnetism in the system, we use these magnetic circuit diagram measurement. It's an optical absorption difference, right, between the left and the right signal of the torus light. So you can think of it as a measurement of optical activities and optical frequencies. And on the left, what I show you is these MCD signals, right? These 3.9 degree just samples, and the 0 and 0. So this vertical axis is the LFQ, right, in the units of the minimum nanometer. And horizontal is just filling number. Again, it means the number of the carriers for the wavy cells. Minus sign means that they put a hole into the systems. So now you look at these phase diagrams. There's a finite phase space. This is now vanishing signal. Okay, so that's my MCD signal. So this just demonstrates indeed, right? We have this spontaneous ferromagnetism. And this magnetism is quite interesting, right? It's a highly now the link and also by electricity. So you have to do as a strong and electric effect. So in the proof, we have this ferromagnetism. We also can fix these say these point and the freezing factor -1. And measure this MCD signal by sweeping the magnetic field, right? Forward and backward, and you see this beautiful hysteresis. So it's very demonstrates the very system is ferromagnetic. Then what we can do is we can take the difference of this green curve and also this orange curve, and you take the difference. The left over is just these hysteretic components. Okay. Then when we talk about this hysteretic component as function of doping, right, is our horizontal axis, and the vertical axis is the magnetic field. So basically, what we see here is the cohesive field of the state has strong filling factor dependence. Now you can clearly see that the cohesive field is already being cast at a filling factor -1, -2/3, and -2/3. These suggest that we already have these fractional state and also integer state that is bigger filling factors. So this just show you an example, right? Optimization itself is already, you know, it's simple, but it's enough to measure this fractional state. So So in order to prove we indeed have this fractionally complex effect, we have to do this transform. If you're familiar with these material systems, right, we know that you already know it's very difficult to make a very good contact to an anomaly or other semiconductors. So my student actually put a lot of effort into this trying to engineer the contact. So the key is that there's two kind of special things we do. The first one is for individual contact, we always pattern a gate. So we can turn on this gate to dump the contact areas and to remove the contact resistance by reducing the shocking barriers. The second thing we do is that for every sample, we actually use an AFM chip to clean the sample surface. Okay? So on the left is the device image you've seen before by AFM cleaning. And on the right hand side is after cleaning. You can see the sample surface already functionality improved. So with this test sample, I show you this a lot of best data with a measurement of the Hall activity. Sorry, the Hall resistance RXY. And we use rule curve. And also use RXX, which is the longitudinal resistance, right in this bracket. Yeah. This vertical axis is the resistivities, and the horizontal is the field numbers. You can see that, right? At the integral field, right here, mass 1, we have this contrast RXY, right? 1 HP squares, and with vanishing RXX. So that's the quantum stop effect. At the fraction field, for example, this magnitude, we have a vanishing RXX, and with nearly contrast RXY, the 3.5 in the units of energy squares. So that's the magnitude curve, right, of CSD. And there's additional depths, like the magnitude fifths, minus 4 sevenths, etc. So those things are now fully developed. Okay. So the next is what we still have room for improvement. And we can also measure this how resistance and as function of the field, right, as we see here. So this just basically showing that we indeed have this analysis how significant tested by the experiment. In addition, you can see is driving contrast out effect. But I think what's really interesting about this is the fixed area is really rich, right? Just by tuning the building field. We can get these very rich fixed diagrams. Here, what I show you is the red one is RXX in the vertical axis of the field. Horizontally is the field number. And the color bar here means the blue color means the vanishing RXX. Okay, red means the very large RXX. And when you see black means it's the large mesh. So by looking at this phase diagram, the thing we identify, right, that each of the fluid mass one, we have this phase space, which is the RXX dimensions. Okay, so that's the point on start date. Then also identify that these fractional fluids, we have these energy RXX as well. We have these fractional point on start date. Then we have the near fluids. We have this suppressed RXX. Okay. And RXY actually is a RXY is the value of 2 actually square exactly 1/2 is. So this state itself actually is an indication of these hospital state, but that is 0 and 3. So these phase diagram is matched by a transform, but it means it's global measurement. And in collaboration with this, are used in optical assisted microwave impedance and capacity. They also match with twist diagram T2. In this case, the local measurement on a ball, and they observe these phase diagram basically the same as we can do in the transform. But these are 2 very different measurements. Shows you the similarities. This is just an example showing that the system is kind of robust. One of the unique feature of the system that I mentioned, right, is tunable basis. The example I showed here, right, the red curve is the measurement by RXX, and the blue curve is XY, and this horizontal axis actually is the field. So you see it's like tunable is like field, right? Starting from 0, right? You have a contrast RXY, with dimension RXX. So we started with this FCI state. And we started tuning the level here. Then this RXX quickly rise and with suppressed RXY. Now we have this phase transition, right? It becomes FCI state to some kind of the state. And how it should. And eventually with vanishing RXY is greater than RXS. So this kind of a state. So an example is that now we can tune the field. We have this beautiful phase transition, right? From this fractional start base to a charge order base, which is how it should. The other feature for this intrinsic feature is that the energy gap is large, right? It has large energy scales. So what I show you here is measurement of RXX as for temperature both at a 0 and Q. So this horizontal axis is the heating factor, vertical axis is temperature, and focus on these fractional fields. So you can see that, right? The depth of this RXX actually has the value to pretty high temperatures. It's minus to the first scale, right? It has the value to about 3 kelvins. So this shows that the state itself has really a lot in that really students are strong in fractions. One more feature along the matching field is the system itself doesn't exactly pan over time. So we know that's the reason we call matching angle to the value. We get a very angle, not to see that you can do it. But that's not the case for these just value and P2. The fundamental reason is that these topologies can come from these layers to being skewed. Okay? So what it means is that as long as you twist these values together, you always have these layers to texture. It doesn't matter which way you are. Okay. So that's why the system is being sensitive to the two things. So what I show you is the measurement of the RXX, its middle column, and this RXY, the bottom column as function of the field, and top just the individual device. So here it's showing several devices from Tristan or 3.9, 0.1 degree to 3.9 degree. They're pretty much similar, right? They all show these renewable component side effect, actually vanishing RXX and with context RXY. So the effect itself actually will be probably extended to about 2 degrees. So we have about a 2 degree fall instead of physics. So at this point, hopefully it needs to, right? We have this fractional formula on top there. Okay, and we're down to this transform influence. And the next question is how can we measure this fractionally sharp excitation, right, in these states? So we know that from fractional how we know that the system is in excitation. The pretty long estimate is that maybe 98, right? But the to prove where the fractional how actually has this fractional sharp excitation is not really fast. It took the community over 20 years to really develop these technology to mention. So here I'll just give you a quick review what's being done in the fractional how community first. Then we can go to talk about these how we're doing this in the aspects. So in the fractional how system, I think the fractional chart was convincingly established by multi-element group by using these potential noise measurement in these one-dimensional channels. Okay, so the key evidence is they show that when these short noise as function current for this one-third state is distinct when you have these charge one channels. Okay, so that's the unique evidence. This is in the fractional chart. Some measurements, for example, using Western tolerance and understanding dots, they build looking at these oscillations, they can figure out the system loss of the therapy charge. Then there's a work from Amir, he has these SCT measurements to measure this basically measure of fractional charge associated with defects. And these actually kind of visible. For example, if you look at these number of levels, these are the integer compound, right? And it's a fraction from 1/3. So you can see there's a 3 times, there's 3 states here. So that's evidence there of fraction charge. So these are really wonderful progress back in the community is celebrating these kind of celebrating these achievements. Then we see inequality that there is a low price for his contribution, right, to measurement of his fractional charge and the other fundamental equation. So fractional charge is one aspect of these units. The other aspect is already mentioned to you, which is the green phase. And one of the early theory or prediction, right, is actually down by Steve Gibson in the 1990s, but we still is really wrong how we can use this measure data of this very phase to tell the sentence there is so how you perform it is a strength in the system in the community to measure these fractional statistics, for example, right? This done at the estimated and this work recently done by Xiaodong and others using this noise measurement from the measure the game statistics. So again, right, what we can see is the original theory is done at the very end. It took about 30 years for the community actually about studies. And the community was Felicia, is also celebrating. There's two gentlemen. One is family as an mentor, both actually adopted price for recent breakthroughs, right? They observe these AM gravity statistics in this fractional process. So I can see that actually some tribute, right, to measure these fraction charge and statistics. Okay. And the system that we were talking to today, it's a zero field and this new system. A lot of people ask me whether I can do experiment. Well, I encourage is I can't. But our material probably takes too loudly to make such a fancy device. Then what can we do? We have a different loss, right? That's all I'm going to today is we can use light and we refer the system we has a fraction charge. It means a zero field fraction. And so I can tell you two things. Like the first is that we observe these triangles actually are fractional charge. So we are fractional triangles and some people will call anyonic. So they say the same thing. And the second is that what I showed you is how we can use these fractional triangles that trust determining these fractional charge. So let me just give a brief background on the topics in case you don't know what it is, right? So you can have a little semiconductor, we're going to use that. When you shine light to a semiconductor, you're going to promote the electron from the valence band to the conducting band. Then these electron holes they actually can bind together through the Coulomb fractions. So you form an excitance. So in this case, right, it's a charge neutral. So in university. Then we also built the system so that say, oh, the effect is not strong enough, then we can form these charged excitons. Okay, so in this case we form trions. So the spectroscopy we can tell these two excitations apart by looking at the investments. So here is an example of the photon investment spectrum of the model wave MOD2. Right, the top here is the PO of unified phenomena, and the bottom is the PO from these trions. Okay, now it's a big energy difference. Okay. So we can tell one is neutral, the other is charged. We can further tell them apart by doing these doping dependence. So this plot is the PO intensity measurement of this model as function of doping these vertices, horizontal energies. Now you see that this chart in the early point, right? We have this little feature here. This is the neutral excitons. And once I started doing the system in the host, then we found these trions. Okay, the trion, right? The energy binding is lower than these neutral excitons because the binding effect. So the energy difference here for model is about 20 little bit over 20 millivolt. So that's the binding energy. And it will come back to experiment a little later. Now we can move on to the shifter values, right? Again, I should have said mentioned, right? As function of filling factor in this vertical axis and the horizontal energies for shifter value around 3.9 degrees. Now you see that these will be different. When I go, okay, you see that there is a fraction fields like -2/5, -2/3, for example, you see that here is clenched. Okay? The clenching of field is suggesting we form these incompressible states. Okay? And then we'll also see that here is clenching back to the last form. So now you can see just use this very simple objects. Right? Just with this measurement, you can already use to do out these fractional states, okay, without the complicated transformations. So the reason I did that, I wanted to because we already proved that, but now we know that for the process is a simple expression to start to manage these states. Then you ask the question, right? So let's look at the the statement. Well, I say that straight just doing two bring down. We know there's a fraction between the states. Meaning there should be anyons. So if there's anyons in the system, we're going to ask this question: whether it's possible actually for these fractional charge actually bound to these charges to form a fractional charge. If we can find them, well, then we can use the capacity expression charge. So what I showed you in the last is indeed we can find such a fractional charge of excitating particles. We can use it as a messenger to weigh out the fraction charge in the system. So again, right, I'm not the first one thinking about a problem with the community, but it was a theory itself that's been there over 40 years. So that's not being done. So here I just highlighted this theory work. I think that in 2000, and this whether it's possible to see these fractional charge excitations being estimated by time and field. I mean, that is a fraction from hospitals. So basically, I'm not going to go through these aspects, but what it says that in special condition, like at least theoretically, it's indeed possible to see these fractional charge excitations. Now the question is whether there's any evidence to it. So this is the latest from in 2006 in Nature Physics. So in this paper, right, they studied the photoluminescence from a panel-only gallium arsenide from wells. So what they see is that I can walk you through, right? Means the radio axis. You turn don't combine magnetic field. Okay? So the state here corresponds to these long fields. And when you tune the magnetic field slightly over these two. And you basically build the system is going to be the mobile fractional charge. Then you see the luminescence has these distinct relationship. Okay, so what is paper, right, and what is paper conclude is that these are signature of the formation of fractional charge charges in the system. Okay, so what they do is they have a company field which is forming certain conditions. But I want you. Right, when you build the system on the edge of the Hall post, actually there will be a register of these luminescent feet. It's a signature of these fractional charge particles. So there's another theory that is basically just appear on that end, right? Now it's a slightly different configurations. So what they consider is that you have a TLD array and put on top of a monoid piece. Depending on the field, that is small addressing can form with the fraction from our space. Now you have this linear instance. So what they propose is that the excitons in these TMD arrays actually can bond to a particle in the brackets and then form a fractional charge. Okay, so this is another proposal. So what we can show you today is that we actually can directly observe the fractional charge. Or finance, just to use so here's the device, right? For cloud, that's on tricks. So for these devices, what's special about it is we have this interface. Okay? So these interfaces between a twisted anomaly and a twisted anomaly on okay? So now we have this interface. So when we shine light to this interface, that's what I got, right? Here's the key testing plot, as I already showed you. Vertical axis feeling, horizontal energies. Now I compare this data with the here I just showed, we found the normal regular just the bias. You can here see the difference. There's similarity. Similarity is that we also see these fractional states in the field, also see these internal states. But the difference is that in addition to these bright main peaks, we have these weak and narrow features resemble what's happening with these main peaks. Okay. Now we're gonna just take a right class at these feeling three quarters. Just look at these left half. You can see there's the main peak, which is bright, we have electrons. Then we have these narrow feature peak, right? Sitting on shoulder. So this actually is the one and after the regular point. So this is the final top edge. Why I cut the trunk point? Well, there's a work to be done. For example, I look at the rhythm state. For the main peak, the lambda on the other boundary is. But for these narrow trunks, lambda actually about 0.2 meters, so it's 5 times narrower than the main trunks. So the community has studied such a path as Thomas says. Yeah, this early work is done in the 2015s, where they studied this defect induced kind of traffic model in the East and observe these narrow field line emissions. And then later on, but the community shows that you can also bring local strains to produce such kind of traps. Then you can see these narrow PO emissions from the system. And very there's work on the edge shows that we can also use FQAH to introduce this kind of trap and introduce these data states. So we did a special mapping on these narrow PO features. And it's the black edge tag indicates the boundary, the interface between the twisted molecule and twisted molecule. Now you can see that the externals actually represent the position of these field features. You can see that, right? They are localized at this interface. So keep in mind, right, this interface, what I showed here, is mapped out by outlets. So I have this special conclusion about the lines. So there's uncertainty becoming aware. But I can comfortably say that this special class in our system, right, it's pretty much along these two interfaces. So now, the first thing I want to do is I want to show that these practices, right, also you can use it to probe these allowable features. So what I did is we just extract the energy of these narrow features, right? These trapped electron states, and then plot it out as functional magnetic field. So basically, I have a second terms. Then I can just extract the positions, right, of the states. And then what I showed is a comparison of these stratospheres. Okay. So from this plot, we basically identify all these fractional chains of states. 2/3 and 4 lines, 2 7 2 essentially. With this chain sequence of this FCSD. Well, this is good. We can use these trapped example in state as fine, right? To probe these fractional states. Then the second is I want to when you just look at this plot, it may, if you really focus into it, you probably see something going on. So let's just zoom in. What I do now is I rotate my axis. Now I make this horizontal axis the spin factor, and the vertical is the energies. But the reason I do this will be obvious in a minute, right? So first, let's just focus on these two vertices. What you see is that when I tune my dome into this third state, the energy actually just plateaus out. That's interesting. Let's remind you of these one-half plateaus, right? I'm not an actual transport, but I give you some similarities so you can imagine. Now, right-hand side is imagined of this RXY, this RXX, right? So we have these sort of plateau here in the optics management. Then, what's really interesting is that when the doping just slightly above these 2/3, the plateau will stop, and a new bright future appears. at a much lower energy. So now I show you there's a red shift of a state, right? This new bright feature only exists using very narrow range. It's a fragile state. Okay, so this state, what we can find is a fractional charge electron state. So just then, as I continue to tune the loading, you'll see there's another shift of the energies, right? The reason is that now I tune the system means now it's how matters this, right? So what you can see that is there's a distinct phase space for these states right here. Okay? But just for the rest of the talk, right, what's considered how the state is fractional trions, and these plateau I showed here it is the FQAH means a trion trapped in the system and the protein is system. So how do I know these fractional trions, right? Well, the third reality possibly is the state only appears in this finite space. Like doubt these fractions, you just start to get these mobile quasi-particles. Then we have these data here, and we have these redshifts. Redshift means feedback with respect to these original CST. And the second is the feature itself actually also appear. So here has these three fifth springs, for example. If we zoom in on this fifth spring, we also see these kind of plateaus, and there's no feature just like that. Okay. And the feature itself is highly reproducible. We see in fast. Here just two examples, right? Let's just focus on the right hand side, right? Where these three fifth spring and some plateau, there's those things like that. And three and two fifth spring and some plateau and these things. So it's highly reproducible across the energy fast. And we can also do the say large field dimensions. So we're seeing here is the zero large field, and see this plateau, this is fractional times. Then when I started tuning up this field, if you remember actually, right, when I tune this field, there's a big conversion from this FCSD to the pathology true state. So you need, right, to start to see that these eventually it wasn't here. So what I can do next is I can just fix my feeling at these processes that I so I can measure these FCA time and also these fractional time at the same time. Right hand side is the part is pure measurements as function of the field. Right? I can use the tune through the field transition from the FCA to this local state. So you can see that this fractional time existing in a similar field range. But with a slightly smaller field. The reason is that when I tune this large field to the near phase transition boundary, the gap actually is unclosed. So when the gap is unclosed, the fraction time becomes unstable. So this just tells us that you need the gap to protect these fragility. Then we can also do counter dependence. From left to right, I increase the counter two now. So we have before you see the states basically melted and together with these states. So last piece I want to mention is I just plot this time diagram in terms of the intensities. Now you see that there's two first things. This bright feature is actually the plateau, and this narrow line here corresponds to these fractional times. So you see that the time and the fraction time, right? They have the same slope. Okay, this is what actually should work. So this demonstrates that this fraction time indeed at the hub, and if they bound to the fraction time, it's exactly as I expected. We should have these two shared slope. So with all these, what I just showed you. Established, the state is bound to a fraction charge, but it is still bounding. How do I assign the charge to state? You can see that there's maybe it's the fraction charge to the state. But what is the charge? So you have to read out this charge. And remember, if I talk to the beginning, I'm going to go the system and the bound is the charge that I'm stating as a red shift from energies. And it's a red shift corresponding to the value that data for that do is we can define the value energy. Now is the union point actually is SCH class. So I can just plot out the spectrum and directly bring out the energy difference. So the value energy of the 2/3 and point actually is 0.8 UAVs. Then I can do something for the 3/5 state. And I can infer, right, the value energy is half UAVs. It's across many different traps, and all the data are summarized in this plot. And these blue dots represents the value energy of these 2/3 fractional times, and these orange dots represents the value energy of 3/5 times. Okay? And then I can give a ratio of the value energy of these 2/3 to 3/5 state, represented by these ring diamond. And here represents the ratio of fractional charge between 1/3 and the 1/5, which is exactly 5/3. So this data shows that, right, the ratio of the value energy of these two fraction states actually is equivalent to the ratio of the fractional charge. 1/3 or 1/5. So that's a strong evidence we have these fractional charge as constants. That's the implication. Six is that the value energy is scale with the magnitude of the fractional charge. So what it means is that, right, as I mentioned again, right, in Bob's paper, what's important is that the fractional charge actually is a function, basically it's a calculus of wave functions. It's calculated allowing wave function intrinsic to that. So if the value energy is a scale of this fractional charge, what it means is that the binding of this charge to these primes, this binding process actually does modify these wave functions. But if the wave function modified, then the binary should not scale with the fractional charge. So that's the indication of the of this result. And so currently there's no theory actually for this work. That is actually is based on observations. So we can go back to these preprint, right? And the work itself is not describe the exact system variable. They also study these fractional charge and translates basically a fractional charge in all attached to the external changes. So these paper, right, and they calculate energies. So what they show is that well, if there's a mobile anyon-trions, right, the value energy is about 80. But if there's a static anyon-trion, so a static means the anyon is bound to a trap that traps it. In this case, right, they will have a about 0.9 degrees, and the value itself is linearly proportional to the particle fractional charge. But even though the theory itself doesn't exactly describe what we do, but I think we can sort of use these, right, just trying to understand what's going on in our systems. Okay, so that's what I'm talking today, but this is a code, right? So I can tell you my vision. What can we do with this, right? I have these chart stage. Right? And we are integrated with these anyonic systems. So just let's say 30 years later, we want to build these quantum chips to make a quantum theory. Okay? Well, then we can use anyons, right, to do simulations. We can use light to read on state to build the instance, okay, to quantum transactions. And what's the beauty of the system is that the energy scale of the state actually is my wave PGs. So we have an ongoing discussion with the electricity, how can we couple the state with these superconducting units using these microwave resonators. So I think that's a pretty exciting direction and we have the quantum systems. So here's a summary, and I think we actually use the we have this fractional quantum also effect, and it's no addition to these quantum Hall families. And again, the community discovered this quantum effect, and a couple of years later, these geological interaction become important. Is discovery of this fractional quantum Hall effect. Then about 40 years later, in this case actually 30 years later, then the integral version of this quantum effect demonstrated as the only field. So that's the quantum effect. And about 10 years later, now we realize it's a fractional version of this quantum effect. But I think what's exciting about this is not just the introduce and our effect in the community. Actually, what I'm excited about is that it's a platform to search new states common matters. Right? We know for this point system, they have a lot of knobs to pure, right? This sample, the fuel, spring, I will show you the alternative we have, right? How can we use the light to actually close the system? So one of the pretty exciting, right, states, actually is posed by the bomb at the 1988. So this is really basically, I think, a prediction, right? Because the other hand is gas. What the bomb proposes is that, well, in certain conditions, actually, the ground state of an gas is a superconducting state. So now we know as alien superconductors. That is not gas. But I feel like now we have all these new systems, and we don't get a field. And I feel like there's for us to realize such big obviously elements in for games. So is that right? I will conclude the talk and acknowledge for students. While we actually see the audience, and he's a postdoc here. And the work actually has a lot of visions, theories, measurements, and still techniques actually, and some of them actually in the audience. And here also how the work we published, also our value has published. Some of them are talked about, some of them I don't have to mention, but I think they're all pretty interesting. And yeah, I'd like to acknowledge the funding agencies for this work, and thank you for your attention.